Welcome back, everybody. We are still in chapter 17, talking about sampling distributions. Um, in our last video, we looked at an example of a sampling distribution of a sample mean. We answered a question, right, about the probability that our sample mean, right, would be less than something or between a certain interval. We know our sample means, right? If we start with any population because of the central limit theorem, we take a sample from that population over and over again. For each of those samples, if we take the mean or the sample mean from each sample, right, and we plot all of those sample means, they will be normally distributed, right, with the same mean as our starting population mean and a standard deviation equal to the starting standard deviation divided by the square root of our sample size. So that's true for the sample mean statistic. It turns out this is also true for proportions, right? So we're going to take a minute here and kind of define proportions, talk about what they are, um, see what requirements we need for them to be normally distributed, for our sample proportions to be normally distributed, and hopefully show a example that'll kind of help clear any questions up that you might have. So uh, if you recall, right, we've talked about this before, but P is our population proportion. This is a parameter, right, because it comes from our population. Um, these proportions, right, proportions that come from our population are not necessarily normally distributed, right? We start with any population. It doesn't have to be normally distributed, but sampling from that population over and over again um, is what gives us our normality, if you will. So then the p hat there is our sample proportion. And this, remember, is a statistic because it is coming from a sample. So our p hat can be written out this way, just as x over n, or our sample size, right? Where this x is the number in the sample with the trait you are looking for. And you divide that by your sample size, right? So proportions are typically calculated from categorical variables, right? So think about eye color is one example of this. If you wanted to take a sample in our class for the proportion of students that had blue eyes, um, X here in that case would be the number in our sample with blue eyes, right? So you would take a sample, maybe it's from our class, maybe we sample 10 students, right? And basically you either have blue eyes, yes, or you don't, right? That's a categorical variable. You fall into one of those two, yes or no. For blue eyes, you would count up the number or the frequency with blue eyes in that sample of 10, right? So let's say 2 students out of the sample of 10 had blue eyes. We would set that equal to 2 over 10, and that p hat, the sample proportion of students with blue eyes in our class, would be equal to 0.2, right? That's just one p hat we could come up with. We could take a second sample from our class, right, of 10 different students, and maybe only one student out of those 10 would have blue eyes, right? So then that second p hat would be 1 over 10 or 0.1. Proportions are always in between 0 and 1. And then here's another example, right? 5 out of a sample size of 40 would be equal to 5 divided by 40, which would be equal to 0.125, which would be our p hat. And then if we were to say 79% of the world's population has brown eyes, well, then we're talking about a population, right? So our p, our population proportion, would be equal to 0.79 or 79% in that case. Okay. Let's go ahead and make this full screen. So now we can talk about the sampling distribution of sample proportions. These sample proportions have a normal sampling distribution, provided we have certain conditions are met. The sample proportion must be obtained from a simple random sample. N times P must be greater than or equal to 5. This is kind of the rule that our book uses, so that's what we'll stick with. You can forget about the greater than or equal to 10. And N times 1 minus P also needs to be greater than or equal to 5. So if you take your sample size, you multiply your population proportion, right? This is a P, not a P hat, so it's multiplying it by the population proportion. That needs to be greater than or equal to 5. And then if you also do 1 minus P, take that number, multiply it by the sample size, that number also needs to be greater than or equal to 5. We'll have an example of this in another video. So the population size also needs to be at least 10 times the sample size, right? So if our population is students at the Winter Park Valencia campus, let's just say there are 3,000 students at the Winter Park Valencia campus, then basically our sample size could not be any larger than 300, right? If our sample size was 301, well, you multiply 301 by 10 and you would get 3010, right? So 10 times our sample size of 301 is bigger than the population size of 3,000. So that's what that requirement is saying. And then just note in your homework, a lot of the times, your homework will call Q, it'll call Q kind of a shorthand for 1 minus P. So in some of these formulas, we're going to have to take P times 1 minus P, or even here, right? Instead of N times this 1 minus P, your homework might have an N times Q, right? And so when you see that Q in your homework, it just means 1 minus P. Okay? So let's take a step back and think about how the central limit theorem applies to our proportions, kind of like we did for our sample means, right? So let's say we take a starting population of this gumball machine, right? And you can see it's got multiple colors. Let's set, really for our trait, let's set x equal to, we're interested in the number of gumballs that are I don't know, let's say that are green, okay? So we obviously don't know the population proportion. We don't know the number of green gumballs in this machine. We might know the total number of gumballs in the machine, but we don't know how many are green, right? We want to try to estimate how many are green. So we don't know what the distribution of these gumballs looks like, but that's okay. So we're starting off with some unknown population, right, of gumballs. But from this population, we can take a sample, right, let's say we take a sample just of size n equal to 5. So we take our first sample, right? And let's plot this out. We'll take samples, right? So maybe we have 0. We'll just go with 0.2, 0.4, 0.6, 0.8, and 1.0, right? So this is our proportion, our sample p hats, right, along the x-axis. And so let's say we sample 5 of these gumballs. Our first sample, we've taken 5, right, as a sample size. So we put 5 on the bottom for our n, which is our sample size. And let's say we get 1 green gumball. The number in our sample with the trait of being green, right, that we care about is only 1. So 1 divided by 5 is equal to 0.2, right? We could make this a dot, or I could make it a little kind of a rectangle, right, square, maybe make it look more like a histogram that we've seen before. And then maybe the next time I get 3 green gumballs, right, out of 5. 3 divided by 5 is 0.6. So I'd put 1 here. And then maybe the next few times I get 0.4. Maybe I get 0.6 again. Maybe I get really lucky, right? It'd probably be really hard to do this, but all 5 are green. Maybe then I get 4 out of 5, right? I get pretty lucky. Again, I get some 3s, maybe some 2s, right? Maybe I get a little unlucky, only get 1 out of 5, get another 0.2. Maybe I get really unlucky, right? And I get 0 here. Basically, what I'm trying to illustrate is that the more that we do this, right, the more normal that our sample p hats will start to look, right? And the same exact way that the total average of all of our sample means was equal to our starting population sample mean. Well, our mean now of our sample proportions, whatever number is here, will be equal to the population proportion from the population that we start with. And the standard deviation, we'll see this on the next slide, should be equal to p times 1 minus p. Perhaps it might be over n, I can't remember, but we will have a standard deviation, right, of our p hats, right? So this again is a distribution of sample proportions. We've sampled many, many times, right, at this point. And the more samples we take, the more p hats we calculate, the more normal this distribution of p hats will get. So the same way our sample means, right, we're starting out from a larger population. We're sampling, again, from a larger population here, calculating a sample statistic. In this case, we're calculating a p hat, right, a sample proportion instead of a sample mean. But these p hats, or these sample proportions, also end up being normally distributed. We'll see on the next slide. Get rid of those beautiful drawings. Excuse me. That the mean of all of those sample p hat values is the population proportion, right? So the mean of all of our p hats, right? If we could take all the possible samples, calculate all the possible p hats, would be equal to the population proportion. And then, yes, the variance of the sampling proportions, right? The p hats would be equal to p times 1 minus p over n, or we could say p times q over n. And that means our standard deviation is going to just be equal to the square root of that. So finally, we can say that our p hats or our sample proportions are normally distributed, right? And they're centered around the starting population proportion with this variance or with this standard deviation. And so now for our z formula, we're going to use our sample proportion that we calculate, just like we used our x bar before. So let me try to draw some similarities here to see if I can help us out. So before we had z, right? Again, for our sample means, it was the x bar, which was the sample statistic that we calculated, over the sigma divided by the square root of n, right? So now we've got p hat in place of our sample mean. We've got a population proportion in place of our population mean. And this makes sense, right? Because now we're trying to compare a sample proportion to the population proportion. Before we were comparing a sample mean to a population mean. And then instead of dividing by the standard deviation over the square root of n, we're now just dividing by the standard deviation of our sample proportions, which is this square root of p times 1 minus p over n. Okay, so these are still normal distributions, so we can still use and calculate z values, right, to find the area under those normal curves. So in the next video, we will look at this example where we're given that 79% of the world's population has brown eyes. So we're given our population proportion, and we'll see if it meets the conditions that we need and find some probabilities as well.